On May 24th, SpaceX officially announced their mission goals for the upcoming 4th Test Flight of Starship. The main focus for this test flight is to demonstrate the ability to return and reuse Starship and Superheavy. As expected, this includes a controlled soft vertical splashdown at Booster 11. And if Ship 29 manages to survive the extreme hypersonic atmospheric reentry heating, then it will continue on to perform its iconic landing flip maneuver, followed by a second soft vertical splashdown in the Indian Ocean. But there was another unexpected detail casually mentioned in the announcement that has become a hot topic of discussion for Starship fans and armchair engineers across social media. This time around, SpaceX has decided to jettison the forward heat shield, also known as the hot stage ring, immediately after the boost back burn, as depicted in this animation by the space engineer and Echo 3D. The question on a lot of people's minds is, if the eventual goal is to achieve 100% rapid reusability, then why would SpaceX jettison the Interstage? If you're one of those folks looking for an answer to this question, then you've come to the right place. In today's investigation, we're going to examine the most likely reason for that decision. After that, we will attempt to determine whether or not this exact situation may have already occurred unintentionally on the previous flight test. My name is Zach Golden, and this is a CSI Starbase Special Report. Hey everyone, welcome and thank you for joining us. Let's get right into it. Why the heck would SpaceX ditch their plan to recover and reuse the Interstage? How does this not go against everything the Starship program stands for? Well, according to the announcement, the reason they plan to jettison the Interstage following boost back is to reduce booster mass for the final phase of flight. So let's start off by looking at why this would be necessary, and then we will examine some other theories, including the plot twist I mentioned in the introduction. Keep in mind, this is a speculative explanation, and the true reason may be different than the conclusions I'm presenting today. The short answer to this question is, as the dry mass of a rocket is increased, the amount of fuel required to decelerate to a safe landing speed will increase as well. Of course, the opposite is also true, as I'm sure most of you are aware. The heavier the payload, the more fuel a rocket will have to burn to reach its intended orbit. Up to this point, Starship has never launched with a payload. For this reason, you will notice that neither the booster or ship are fully topped up with fuel during these test flights. So once SpaceX begins performing missions with a payload, we'll likely see these tanks filled to capacity. The difference between launch and landing is that the booster is never going to land with a payload. So there is no need to adjust fuel levels for landing because the mass will always be the same. It's important to note that the booster is not designed to use its main liquid oxygen tank at all during the landing burn. Instead, it uses a large header tank, which I will refer to as the landing tank throughout this episode. There is no header tank on the methane side. Instead, the massive downcomer with a sump filter on top is used to perform the same function. As a result, it doesn't have the same limitations as the liquid oxygen landing tank and won't be relevant during this discussion. I described the internal plumbing of the booster's LOX tank in my most recent episode, so if you would like to get a full understanding of how it's designed to transition from the ascent mode to boost back mode and then landing mode, make sure to watch that after this. That episode also includes an in-depth analysis of literally everything you could possibly want to know as it relates to hot staging on the Starship. For the purposes of this episode, what you really need to understand is that the landing tank is specifically designed to be completely filled with liquid oxygen. In order to guarantee an uninterrupted supply of propellant, you have to make sure that the liquid remains at the bottom of the tank. If the tank is only partially filled, then as the booster is falling through the atmosphere, the fluid would have a tendency to shift up towards the top of the tank. After initiating the landing burn, the engines would begin pulling gas through the turbopumps until the upward acceleration causes the liquid to fall back to the bottom. Unfortunately, by that point, it would already be too late, and the engines will either destroy themselves or automatically trigger an early shutdown due to the disrupted propellant supply. To prevent this from occurring, it's important for the landing tank to be completely topped off prior to launch. Once full, this is basically all the liquid oxygen available for the landing burn. Any residual liquid left over in the main tank will not be available to the engines once the booster is swapped to landing mode. So if this header tank happens to run dry during the landing burn, hopefully it's over water, because if not, then you can probably expect a crash landing at the launch site. During the Everyday Astronauts tour of Starbase back in 2021, Elon mentioned that the booster will have roughly 20 tons of residual fuel upon landing.
And then you got propellant residuals, which might be on the order of 20 tons too.
Okay.
So,
At first take, that may sound like there should be enough extra fuel to extend the landing burn if necessary. But keep in mind that this 20 tons of fuel will be split between the methane tank, main oxygen tank, and the landing tank. Given the 3-to-1 ratio of fuel consumption by the Raptor engines, let's assume that there will be 5 tons of fuel remaining in the methane tank and 15 tons of oxidizer split between the main LOX tank and the landing tank. To avoid damaging the 13 center engines, it's equally important to not run out of fuel during boost back as it is during the landing burn. So let's also assume that there will be 12.5 tons of LOX left over in the main tank and then 2.5 tons in the landing tank. For those who are wondering, the values I went with here are just a super rough estimation based on the ratio of delta V required for the boost back phase versus the landing phase. So we have 2.5 tons of extra liquid oxygen available for the landing burn. With this in mind, let's consider the fact that when engineers were designing the landing tank, they likely expected that the mass of the booster would not exceed 250 tons and calculated the size of the tank they would need based on that information. In other words, the tank should hold just enough liquid oxygen for a 250-ton booster to initiate a landing burn 5 kilometers above the landing zone and decelerate from 2,000 kilometers per hour down to 0 with 2.5 tons of LOX remaining after shutdown. As I said before, these are not the exact numbers. I'm simply estimating these values using the limited information available to us for the sake of this explanation. All right, now here's where the problem arises. Because of the rapid pace of manufacturing at Starbase, this landing tank design was identical for boosters 7, 9, 10, 11, 12, 13, 14, and 15 prior to the first integrated flight test. Shout out to the Ring Watchers for keeping track of all this. This is the production tracking diagram from May 1st of 2023, which was 10 days after IFT-1. Because of how far ahead they were into production at the time, it was already too late to make changes to boosters 7 through 12, aka Flight 1 through Flight 5 boosters. The problem is that in the 13 months between Flight 1 and the upcoming Flight 4, several important changes were made which resulted in a significant increase in the dry mass of the booster. First, SpaceX realized that they needed to increase the amount of engine shielding for the outer 20 Raptors. This meant doubling the amount of paneling in the containment boxes used to isolate the engine power heads and protect the adjacent engines from explosions. To prevent fuel leaks inside of the enclosures from turning into bombs, they drastically upgraded the onboard fire suppression system. This resulted in another mass penalty after they swapped out 4 relatively small CO2 tanks for 2 massive tanks with 15 times the capacity. This required larger aero covers to be installed over them as well. Next, they introduced the now infamous hot staging maneuver, which meant incorporating an insanely heavy forward heat shield interstage. We know from the revised PEA report released prior to IFT-2 that this hot stage ring weighs at least 9 tons. I'm actually going to round this up to 10 tons, because I believe these numbers may have been reported before the first Flight Ready article had been produced. There were a lot of additional structural supports that were added to the final version of the design after they completed structural qualification testing of the test article. After the catastrophic engine failures that occurred during the boost back burn on Flight 2, SpaceX added additional slosh baffles to the bottom of the liquid oxygen tank. Those of you who have seen the episode I mentioned earlier will remember the simulations created by Ryan Hansen Space to show the severity of the fuel sloshing experienced by Booster 9 after stage separation. This upgrade is intended to mitigate that problem. Unfortunately, we have no idea what the new baffles look like, but Ryan compared several different variations of possible designs based on the clues visible on the outside of the tank. For the sake of time, I'm not going to re-explain that part again in this episode. In the end, these simulations seem to prove that the only way to effectively restrict the upwards motion of the liquid and keep as much on the bottom as possible was for the baffle to cover the entire cross-section of the tank. As you can see, it actually resembles a colander more than it does a slosh baffle. For this to work, there must be enough holes through the baffles for the propellant to pass through without restricting flow to the engines. We believe these baffles may have also been intended to help prevent ice from reaching the bottom of the tank. There are intake filters on each of the liquid oxygen inlet valves, which can become clogged if they end up covered in ice. Trapping the ice above and between the plates should help reduce the likelihood of engine failures due to clogged filters, which actually ended up still being an issue during Flight 3. If it became necessary, the holes could be made smaller but more numerous to help trap the ice more effectively. Of course, it's also entirely possible that these two baffles look completely different from what's shown here. Either way, we know they are very large and likely have a significant mass penalty. Finally, On B-11, which is the booster that will be paired with Ship 29 for Flight 4, SpaceX tripled the number of vertical stringers in the methane tank. Previous boosters had 24 stringers stretching the entire length of the tank, whereas B-11 now has 74 stringers. The purpose of this is to increase the structural stability of the tank while unpressurized. So as you can tell, the Superheavy booster has most definitely put on some pounds. Well, more like tons. In fact, you can probably consider it to be obese. Again, we're totally guessing here, but for the sake of this explanation, let's just say that the total increase in dry mass from booster 7 to 11 is somewhere in the area of 25 tons. With an original mass of 250, an additional 25 tons is equivalent to a 10% increase. As much as I would like to do the math to correctly determine how much additional fuel would be needed to compensate for a 10% increase in mass, I'm not an aerospace propulsion engineer. And even if I was, I think there are too many unknown variables that need to be factored in to get an accurate estimation. Instead, we're going to drastically oversimplify this and say a 10% increase in mass requires 10% more fuel in order to bring the booster down to a safe landing speed. In reality, this is probably not a direct one-to-one correlation. But the point is, if the landing tank was designed to carry an additional 2.5 tons of LOX, and that 2.5 tons just so happens to equal 10% of the total capacity, then this extra mass would not be an issue. Although if that were the case, it would definitely be pushing the boundaries. And there would be a risk of running out of fuel earlier than desired. If this 2.5 tons of extra margin is actually closer to 5% of the total capacity, or maybe even less, which I think is more likely, then now we are in some trouble. So if this is the situation that SpaceX have found themselves in, then what can they do to resolve it? Well, the ideal solution would be to increase the size of the landing tank. But as we mentioned earlier, that design has already been locked in at least up to the Flight 5 booster. With that said, the only other alternative would be to shed some extra mass in order to safely land this thing. The only way to do this would be to jettison the hot stage ring after stage separation. This should reduce the mass of the booster by up to 22,000 pounds, or 10 tons. So let me know what y'all think. Is this why SpaceX has made this procedural change for Flight 4? Without an official explanation, this is the best that I'm able to come up with, but I'm looking forward to reading through your opinions in the comments. Now, anytime we're getting heavy into speculation like this, I always try to include some sort of counter-arguments. After discussing this theory with Jax from the Ring Watchers, he's confirmed that the landing tanks that have been spotted for boosters 13 through 16 are virtually identical to the ones used on boosters 7 through 12. Well, this definitely throws a huge wrench in this theory and can only mean one of two things. Option 1, SpaceX has chosen to ignore this issue for now and continue ejecting the hot stage ring all the way through Flight 10. If so, then it will probably be addressed on Superheavy V2 and V3, which will feature larger fuel tanks and most likely larger landing tanks as well. It seems that SpaceX is confident that they will soon reach a level of reliability with the Raptor engine that will allow them to ditch the engine shielding entirely. This would make the fire suppression system unnecessary as well. That alone will eliminate at least 10 tons of extra mass, if not more. And of course, option 2 is that this theory is totally incorrect and there's something else entirely different going on here. If that's the case, let's explore an alternative explanation. Welcome to the plot twist. This alternate theory stems from a post that I made on X immediately after SpaceX revealed their plans to jettison the hot stage ring for Flight 4. In that post, I mentioned that I believed it was likely that SpaceX already did this on Flight 3. To be honest, some of the feedback I got was pretty negative, and a few folks were not happy with the way I phrased that. It's true that my reasoning for this statement was partially related to a few rumors that have been floating around, but more importantly, in my opinion, if the landing tank theory is correct, then it wouldn't make sense for SpaceX to have kept the hot stage ring attached during Flight 3. If they were already aware that the extra mass would prevent them from perfectly simulating the conditions required to land a booster on the chopsticks, then why not take the necessary steps to mitigate the problem? As far as I'm concerned, the most important goal right now is for SpaceX to demonstrate the booster's ability to reach a predetermined position and maintain that position for the length of time that would be required for the chopsticks to close. The sooner they can accomplish that, the sooner they will be able to move on to the real thing. But one thing I didn't consider, which is a very good point made by Ryan Hansen Space, is that no matter what the current limitations are, SpaceX will eventually want to land with the interstage still attached. If not, they will never be able to claim 100% reusability. For that reason, it's important to gather data as soon as possible to determine how the guidance system and grid fins will perform with this 10-ton interstage attached to the booster. Not only will this hot stage ring shift the center of gravity, but the cutouts through the external surface could significantly change the aerodynamic properties of the booster as it's descending through the atmosphere. So the question is, Even though there was no mention of this in SpaceX's statement regarding Flight 3 issues, is there any way for us to prove that the hot stage ring was actually separated from the booster during that event? Well, in my opinion, the answer is yes, but in order to do so, we're going to literally have to chase some shadows. Let's start off by analyzing the footage from the official SpaceX broadcast, since that's really the only evidence available to us. Beginning shortly after stage separation during the boost backburn, the first thing to take note of is the position of the sun, which is almost directly in line with the aft section of the booster. This will be important for trying to recreate the shadows in a 3D space. Roughly 15 seconds after an unexpected early termination of the boost backburn, the booster begins performing its flip maneuver to reorient the aft section so that it's pointing towards the landing zone. As the booster is pitching forward, one of the first identifiable shadows that we can see is from the grid fin located behind the camera. As the booster continues to rotate, you can see the shadow transition down to the lifting pin on the bottom left corner of the screen. The next shadow that we see becomes visible 6 minutes and 30 seconds into the flight. Looking at the bottom right corner of the screen, we can see a small shadow appear on the side of the grid fin. With a little help from this recreation by Chameleon Circuit, we can easily determine the source of the shadow. Looking at the hot stage ring from the front, you can see that there are several stringers on the external surface of the interstage. Looking at it from the side, let's take note of the outline of the bottom of the stringer. When we rotate back to the view from the onboard camera, you can see that the shadow from that same stringer is being projected onto the side of the grid fin. Thanks to this, we can confirm that at 6 minutes and 29 seconds into flight, that the hot stage ring was indeed still attached to the booster. For the next 21 seconds, there are no additional shadows that we can attempt to identify. But at the 6 minute and 51 second mark, the grid fin tilts down in the direction of the camera, and we can see a diagonal shadow appear in the bottom left corner. Thanks to the space engineer, who was the first person to reanalyze this footage after my post on X, we can examine the significance of this shadow. Because we already know the position of the sun at this time, we can recreate what this shadow would look like if the hot stage ring was still attached to the booster. When we compare that to what this same shadow would look like without the hot stage ring attached, you can see that the shape we are seeing here seems to strongly resemble what we would expect to see if the interstage was no longer present. Alright, so if what we're seeing here is real, then the next question that most of you will probably be asking is, why would this happen? Was it intentional or accidental? Well, as we mentioned earlier, based on the mission procedure for Flight 4, we know that SpaceX plans to jettison the Interstage immediately after the completion of the boost backburn. In this case, however, the hot stage ring seems to have disappeared more than 3 minutes after the boost backburn. This is probably a good sign that this was not intentional and likely unexpected. If this is the case, then the only way this could possibly happen would be a failure of the stage separation clamps. Let's take a quick look at how these work. The current version of Starship has 2 sets of stage separation clamps. One set to mate the interstage with the booster, and the other to mate the ship to the interstage. The clamping mechanism is surprisingly simple, consisting of a relatively small latch that flips out of the alignment housing into its locked position. The first group of clamp actuators are tucked in against the inside edge of the booster's forward section. We aren't 100% certain what they look like, as the design was changed after Booster 7, and we've never been able to see them again from this angle since they did that. Just for transparency, in this situation by we, I mean the ring watchers. Prior to the change with Booster 7, there was a large spring pushing up on the latch to hold it in the locked position. To release the clamp, the hydraulic actuator is used to pull down against the force of the spring. The present design is likely something similar, but with an electric actuator instead. This clamp latches onto the receiving end on the hot stage ring. It's basically a thick plate welded to the inner wall of the ring. When the interstage is lowered onto the top of the booster using the alignment housing to guide it into place, the spring-loaded latch snaps into place. As I said, this is incredibly simple, and it's hard to believe that 3 of these clamps are all that are keeping the interstage attached. But it clearly works very well considering the fact that Booster 7 and Ship 24 managed to remain attached while performing multiple supersonic backflips during IFT-1. Directly above the receiving end of the clamp on the interstage, there's an identical actuator which interlocks with the receiver on the aft section of the ship. Both the lower receiving plates and the actuators for the ship clamps are enclosed inside of boxes with protective covers over them. Without this cover, you would likely be able to reach down through the alignment housing and touch the top of the actuator. With that explanation out of the way, let's move on to the possible mode of failure for these clamps. During stage separation, there is an extreme amount of thermal loading on the interstage as a result of the exhaust plumes from 6 Raptor engines firing at point-blank range. Second stage ignition is incredibly violent, and it's probably safe to compare it to detonating a bomb inside of a partially confined space. It's possible that this overpressure event could have damaged the protective cover and allowed the hot gases to penetrate down to the clamp actuator through the alignment housing. If at least 2 of these actuators are somehow damaged during the hot staging event, it would be very difficult for the remaining clamp to keep the interstage secured in position. It would likely be fine during the boost back phase where the G-forces from the engines are helping to keep it pressed down against the top of the booster. But once the booster reorients itself for re-entry and begins descending through the denser layers of the atmosphere, the only forces keeping the interstage from flying away would be its own weight and that single clamp. Returning to the in-flight entertainment, at this point in time, the avionics computer is probably thinking to itself, damn, we really just lost 6 out of 13 engines during that boost back burn. So our ability to stick the landing is going to be significantly compromised. It's all good though. In the meantime, let's just focus on hitting the target. At first, everything seems fine. Booster 10 is falling through the stratosphere and is traveling on a very stable trajectory. The grid fins are doing a great job guiding the vehicle and can be seen making very precise course corrections. At the 6-minute 30-second mark, we see that first shadow which gave us confirmation that the interstage is still attached. 7 seconds later, B10 passes through the clearly visible boundary of the troposphere and begins approaching a thin layer of altocumulus clouds. It's important to note that these altocumulus clouds are typically associated with high wind speeds and significant levels of turbulent airflow. But Falcon 9 travels through high upper atmospheric winds all the time with no problem, so this really shouldn't be an issue. Unfortunately, this is likely when the aerodynamic forces began lifting the hot stage ring away from the top of the booster, because the moment it passes through the clouds, the avionics system says, "Wait, what the f***?" and immediately begins freaking out. It knows something is wrong, but it has no idea what it is and begins making huge corrections with the grid fins. At 6 minutes and 51 seconds, we see the second shadow confirming that the hot stage ring is no longer present, but at this time, it's too late because the damage has already been done. For an unknown length of time during this 20-second window, these extreme forces were acting on the bottom of the interstage while it was still partially attached. In the process, it managed to completely destabilize the booster before it finally ripped free from the remaining clamp. Looking at the grid fins, you can see several massive overcorrections as the vehicle is struggling to regain control. In my opinion, it appears that it does eventually begin to stabilize itself. Unfortunately, we can't say for sure, because moments later the signal was lost and the booster slammed into the water at a speed of 1,100 kilometers per hour. Had they successfully initiated the landing burn, I think the 13 gimbling engines would have been able to provide some additional assistance, and there's a good chance Booster 10 would have made a full recovery. It may not have landed in the precise location it was intended to, but it probably would have managed a controlled soft touchdown. If this situation occurred as described, then the Superheavy engineering team may need to rethink the design of the clamp mechanism to guarantee it will never again fail to keep the interstage attached to the top of the booster. At minimum, they would have to find a way to better protect them from becoming damaged by the violent exhaust plume during hot staging. In the meantime, it's probably best to completely eliminate the possibility of a repeat incident for now to ensure that SpaceX is able to successfully demonstrate a precision landing on the next flight test. Doing so will allow them to move on to the first return to launch site landing on the chopsticks as soon as possible. At the end of the day, it's probably a good thing this occurred when it did instead of during a future mission. Even if the booster managed to recover, who knows what damage could occur if the hot stage ring came down somewhere near the launch site.
Don't get me wrong. Being able to eventually return with the interstage still attached is certainly important. That's the only way they will have a chance to study the aftermath and determine whether or not it's been damaged beyond the possibility of reuse. From there, they can improve the design based on what they learn. For now, I think it might be more important to achieve 95% reusability and then worry about that other 5% later. Once again, I want to remind you all that everything said in this episode is simply evidence-based speculation and should not be taken for a fact. Without official confirmation from SpaceX, this is the best that we can do. Who knows, maybe we'll get lucky and Elon will decide to release the footage if he ever happens to watch this episode. Either way, I want to say good luck to the SpaceX team for the upcoming test flight. It's incredibly awesome having front row seats to be able to follow this development process as closely as we do. This level of access doesn't really exist anywhere else in the world, and we can't thank you enough for giving us all something to get excited about every day. If you're new to the channel and found yourself enjoying this type of in-depth analysis, then please consider subscribing if you haven't already. I currently have about 4 episodes in various stages of completion that I'm really excited for, so be on the lookout for that. If you'd like to further support what we do here, then we would love for you to join as a member of the channel or become a monthly supporter on Patreon. Before we go, I want to give a huge shout out to the space engineer for his awesome shadow hunting work, which pretty much enabled this episode to happen. Make sure to follow him on X if you haven't already. You can find a link for that in the description below. Huge thanks to Chameleon Circuit, Ryan Hansen Space, and Andi, the creator of the Starbase Sim video game, for their direct contributions to this investigation. Of course, special shout out to Jax from the Ring Watchers and the team of CSI Starbase agents in our Discord server for assisting with research as always. Last but not least, thanks to all the other photographers and content creators whose footage was used in today's special report investigation. You can find links to all of their various platforms in the description as well. With that, my time is up. Until the next deep dive investigation, this is Stage Zero Zach, signing off.